Okay, so maybe I should just introduce myself because maybe I'm less known. I'm Renato Renner and I'm going to chair this session. And then I'm now giving the floor to Leonard Susskind for the first talk of the afternoon. It will be the only talk today. We made an exception.
Okay, so I'm actually reading now. I asked for 3 minutes or 2 extra, so for a word or 2 of explanation, and I do mean 3 minutes. I woke up this morning intending to spend an hour before the lecture, finishing up the details at the end, but I discovered that the congressional hearings started at that time. Now, while I firmly believe that my lecture today will be far more important to the future, a trillion years from now, than anything taking place in Washington, in the short run, the congressional hearings are more important. So I commend anyone who opts out to watch them. You have my blessing. If Arthur or anyone else would like to set up a link, I'd be glad to do a do-over. A little more polished maybe for those who perhaps do want to watch those congressional hearings. Arthur, I thank you for inviting me. As I'm sure you know, I'm not a mathematician or even a mathematical physicist as the field is defined today. But nevertheless, there have always been strong links between my work and mathematics. And I think the same is true of what I will tell you today. Incidentally, I am not going to talk about complexity today. It's not that I don't think it's important or interesting. The subject, at least in its connection with black holes and the physics of quantum gravity, is now almost 10 years old. I have put out Princeton lectures, other lectures, and I really don't have too much more to say about it. I've been very preoccupied by another class of questions. And so let me share my screen. What did I do? Hold on. I think, yeah, screen sharing. Screen broadcast, start broadcast.
We see it now.
Can you see my screen? You see it?
Yes.
Okay, let me just clean it up a second. Templates, apply. Okay, what I'm going to talk about today is double-scaled SYK. A few of you know what SYK theory is. If you don't, I'll try to tell you. Infinite temperature, something called temperature, and de Sitter space. There'll be no higher mathematics in this talk. There is a higher mathematics version of it. It involves von Neumann algebras, and I strongly recommend the paper that's about to come out by Witten and his collaborators, which should be out in, I hope, a few days, which parallels many of the things I'm going to say. My own style, as I said, I'm not a mathematical physicist. I don't think like a mathematician. I tend to think more like an auto mechanic who's trying to figure out what's wrong with the car. Okay, de Sitter space. There's lots of opinion out there by theoretical physicists about what de Sitter space is or isn't. De Sitter space is in the swampland. De Sitter space requires ultra fine tuning. De Sitter space has a Boltzmann problem, whatever a Boltzmann problem is, don't worry about it. The symmetry of de Sitter space, OD1, is inconsistent with finite entropy. De Sitter space is unstable. All of this is trumped, excuse me for my language. Yes, Trump has another thing, is trumped by a simple fact, and that's that observationally, the universe is tending toward de Sitter space. We live in something which in time will become very close to de Sitter space. Of course, it could be wrong, but that's the way it's going now. We urgently need a concrete, tractable model to investigate the kind of claims and to investigate the nature of the connection between de Sitter space, cosmological space-time, and quantum gravity, quantum information, all the things that we've been studying in another context. So let me begin with the holographic principle. The holographic principle says, we can put it this way, if we take a nested set of spatial regions, each bounded by its own boundary, with some restrictions, some convexity restrictions, which I won't go into, then the boundary of each region has enough degrees of freedom in a holographic sense to describe everything within that region, and not enough to describe anything outside that region. ADS-CFT is a special case. It's a special case in which the geometry is asymptotically, for the most part, anti-de Sitter. There's a picture of a spatial slice of anti-de Sitter space. And if we want to describe the whole space, we need to put the hologram, let's just call it the hologram, out at the boundary where the area is largest. What about de Sitter space? All right, I've written down the metric of de Sitter space. If you know it, you know it. If you don't know it, you don't know it. And I don't think you're going to learn it from my lecture today, so I'll just jump over it. There it is. There it was. Here are two Penrose diagrams. Let me not give away the punchline. There are two Penrose diagrams. They're completely different geometries. The left one is the two-sided black hole, the two-sided ADS black hole, so-called two-sided black hole. And the right side is de Sitter space. Notice that they look exactly the same. They have exactly the same causal structure, but the geometries are completely different. Let me get my laser pointer out here. Yeah, okay. To see the difference, you can just imagine slicing them through the t=0 section. What you see in the ADS two-sided black hole system is a wormhole, which terminates out at the boundaries with an infinitely large boundary. The infinitely large boundary is just the boundary of the de Sitter space, anti-de Sitter space, excuse me. On the other hand, if you slice through the interior of the de Sitter space, what you see is quite the opposite. Oh, incidentally, the dotted line here is the horizon. The dotted line here is also the horizon. And in fact, the horizon of static patches. Static patches, I will leave it to you to look up if you don't know what they mean. Okay, so de Sitter space and anti-de Sitter space are very different, despite the fact that their Penrose diagrams are identical. Now, how does this difference affect the holographic description? Well, sorry. Where shall we put the holographic description, the holographic degrees of freedom of the anti-de Sitter space black holes? We want to put it out where the area is largest, so that those degrees of freedom encompass everything within. For the anti-de Sitter case, that means putting the holograms out at the boundaries, or as close to the boundaries as we like to get them. On the other hand, for this, and notice that that is not at the horizon. The horizon is where the area is smallest. By contrast, in de Sitter space, the largest area is where the horizon is. And that is the place where the rules tell us to put the holographic degrees of freedom. Well, that's quite a difference, and it accounts for much of the difficulty in understanding the holographic description of de Sitter space. The de Sitter space hologram is on the horizon. Or what does physics look like in de Sitter space from the point of view of an observer as far from the horizon as possible? That would be the fellow over here, for example, Bob. Alice, of course, is over here. Forget Alice. Bob is over here, and he's looking at the world. He looks out away from him, and he sees the horizon. What does that world look like? Well, here's again, Bob. Oh, darn, this thing jumps around too much. I think I know why. Okay. He looks around him, and he sees a horizon out at the boundary of his observable region of space. Here he is, Bob, right there. I'm sorry. What does he see within the region accessible to him? don't know why this is jumping around. What he sees is a kind of thermal distribution of quanta, very, very low energy quanta. He sees a world which at its boundaries has an entropy, or in fact, a world that has an entropy, and that entropy is proportional to pi over g times the radius of curvature of the de Sitter space. He also sees a world in which there's a Hawking temperature, which is 1 over 2 pi L, which is incredibly small if L is 10 billion light years. And altogether, he sees about 1 thermal quantum, 1 photon or graviton of wavelength equal to the de Sitter radius, except out near his horizon, where things get hotter. Now, what is the physics that the quantum mechanics of de Sitter space will be telling us about? It will be telling us about fluctuations, thermal fluctuations to be sure, but also other kinds of what we can call out of equilibrium fluctuations, fluctuations which are large scale. For example, a fluctuation may happen in which in the interior of the static patch, a black hole nucleates. One knows how to calculate the probability for this. The probability is e to the minus the entropy deficit. The entropy deficit is the decrease in entropy due to the presence of the black hole. Now, you might think that the black hole increases the entropy of the state, but that's not true, because what you find, if you go back to the original picture, what you find is the nucleation of the black hole shrinks the cosmic horizon. This picture here is a little bit smaller than this picture. It pulls in the cosmic horizon, and it pulls in the cosmic horizon enough that it decreases the area more than the black hole increases the area of horizons. And the result is that the probability for the nucleation of anything is e to the minus the entropy deficit, and the entropy deficit must always be positive. Another way to say that is that the vacuum or the empty de Sitter space, it's not empty, it has some thermal quanta in it, but it has the largest possible entropy, and all fluctuations away from that have smaller entropy. One can calculate very easily the probability for the nucleation of such a black hole, even if it were just a black hole of Planckian mass. The probability for the nucleation of it would be e to the minus 10 to the 61 in units in which m is represented in the Planck mass. So these are incredibly rare fluctuations, but in fact, they're all that really happens in de Sitter space. And that is what a theory of de Sitter space will be telling us about. Okay, so now let me come to SYK, the so-called SYK theory. The SYK theory is a holographic theory, which is describing a bulk theory, which is called JT gravity. J for Jacques, T for Teitelbaum. And it is a theory in which the geometry is almost one-dimensional. Instead, it's not really one-dimensional. It's a long, thin wormhole, if you like, or a long, thin throat connecting to asymptotic or almost asymptotic boundaries. Being a version of anti-de Sitter space, the hologram is at the boundary, not at the horizon. And we know in that case exactly what the holographic degrees of freedom are. They are the quantum mechanical degrees of freedom of the SYK system. If you don't know about SYK, you won't learn here, but I will just for completeness write down what it is. It's a theory in which the holographic degrees of freedom are Majorana fermionic degrees of freedom called chi. There are n of them, where n is large. There are a set of coefficients, J1 through JQ or JIQ, and the Hamiltonian is a sum of monomials of the chi's up to powers Q. You could say this Hamiltonian is Q local. Q local roughly in the same sense as you sometimes use the word K local. They consist of monomials. You can call them gates, I suppose, but let's just call them monomials up to power Q. In fact, just of power Q. Majorana fermions have anti-commutation relations, and the J's are drawn from a statistical ensemble. The statistical ensemble, something like random matrix theory, but a statistical ensemble which is characterized by a variance. Each one of the J's has a variance, which is Q factorial. Remember what Q is. Q is the size of the monomials. Q factorial divided by n to the Q minus 1 times a parameter, an invariant parameter called fancy J, calligraphic J squared. The other thing about the SYK JT theory is it's evaluated at very, very low temperature. Temperature much smaller than the characteristic energy scale J. That's SYK JT. I maintain, and I will try to show you some of the reasons why, that there is another limit of the SYK theory. DS does not stand for de Sitter space here, but it could. It stands for double scaled. The double scaled limit, like the original version, is also a large N theory, large number of Majorana fields. We can think of it as N goes to infinity, but instead of Q squared being fixed, Q squared grows with N. Q squared grows with N like a constant lambda times N. Now, this should remind you of something else. If you're familiar with gauge theories, then there is a so-called 't Hooft limit of large N gauge theories in which a parameter called alpha, the 't Hooft coupling constant, is equal to G squared times N, or alpha over N is equal to G squared. The equations are somewhat parallel, and in fact, I maintain that the perturbation theory of the SYK theory looks enough like the perturbation theory of large N gauge theories that a correspondence is warranted. In particular, Q squared is like alpha, the 't Hooft coupling, N of course is like N, and lambda is like G squared. We will come back to that. Well, if I have time, we'll come back to it. But the other main ingredient which makes DS SYK as a theory of de Sitter space entirely different from the JT from the other version is that the temperature is not low. The temperature is in fact infinite. I will come to the reasons or some qualitative reasons why we think the temperature is infinite. But first of all, let me say what I mean by the temperature. The temperature is a technical parameter which appears in the Boltzmann distribution, that the density matrix of one side, when you integrate out the other side, the density matrix of the static patch is e to the minus h over t. I haven't normalized it. Of course, there's a partition function in there. That the density matrix at infinite temperature is just the identity matrix, the maximally mixed density matrix. The argument for this, there is a technical, I said there would be no higher mathematics. I will tell you that, and I recommend strongly when the paper comes out, take a look at it. It's a paper by three authors, one of which I'm sure you're familiar with, and it's on type 2 von Neumann algebras as the right framework for thinking about de Sitter space. The things that it says are very, very close, if not identical, to the things I will be telling you about by Lynn and myself. I could have tried to give this lecture in the language of von Neumann algebras, but I would not have been true to myself had I done that. Nevertheless, I think there's a great deal of value in comparing the two approaches, my own approach, which is that of the car mechanic, and the more mathematically minded people. Okay, so let me tell you though, what it is that makes me think the temperature should be infinite. Here again is the Penrose diagram, and now I'm thinking of it as a Penrose diagram for de Sitter space, but I'm also at the same time have in the back of my mind the JT gravity description. In the JT gravity description, at low temperatures, very, very low temperatures, where the temperature is much lower than J, there is an almost asymptotic boundary over here, an almost asymptotic boundary, which as T gets lower and lower, temperature that is, moves more and more close to the boundary of the Penrose diagram, in such a way that the length of the throat at low temperatures becomes longer and longer as T goes to 0. That's the usual limit of SYK JT, where the asymptotic bound or the semi-asymptotic boundary, it's also called a Schwarzian boundary. You know more about Schwarz than I do. The Schwarzian boundary is way out near the boundary of the Penrose diagram. If you take temperature of order J, by contrast, you will find that the Schwarzian boundary has moved into somewheres in the interior of the Penrose diagram, but nowhere near the horizon. Now, the Schwarzian boundary is another word for where the hologram is stored. So by going to the other possible energy scale in the problem, not the inverse temperature, but J itself, one would find that the holographic description would be located somewheres midway between the boundary of the Penrose diagram and the horizon. That would mean that that holographic description has enough degrees of freedom to describe everything in here, but not everything back here. Remember, in de Sitter space, the area shrinks as you go to this point. The only way to capture enough degrees of freedom to describe the whole static patch is to move the Schwarzian boundary almost into the horizon itself, and that corresponds to a temperature much larger than J. In the limit of a very large de Sitter space, it essentially means temperature infinite. The same conclusion, essentially the same exact conclusion, is reproduced by the analysis of type 2 von Neumann algebras. I could explain that, but I will let Witten and his collaborators explain that. Okay, given that setup, double scale SYK at infinite temperatures, what can we say about the physics of it? And what can we say about why do I think that it's a good description of de Sitter space? So let's see how we're doing. Okay, let me come to the phenomenon of scrambling. The phenomenon of scrambling is a key phenomenon in explaining both how information spreads over a quantum circuit and how things fall into a black hole. They are related to each other. Okay, here is what information scrambling means for our context here. Supposing you perturb a simple holographic degree of freedom. In that case, this could mean one of the Majorana fermions describing the boundary theory. With time, that operator evolves as a Heisenberg operator and becomes more and more complex as a system of Schrodinger operators. In fact, the single operator chi will evolve into a big polynomial of higher and higher order in chi as time goes on. The order of that polynomial, or let's just say the average size of that polynomial, the average order of it, is called the size. That's what people in this business now call it, the size. And the size grows exponentially. It grows exponentially, just as indicated here by this growth phenomena here. One fermion becomes 2 fermions, becomes 4 fermions, and so forth. But that can't, when I say that it becomes, it's another way of saying that the perturbation on one fermion influences 2 fermions, influences 4 fermions as time goes on. There's a technical way of describing that. I won't get into it now. The size grows as e to the 2 pi over beta. Beta is the inverse temperature. Remember, beta is very large, temperature is very small, times time. And the system becomes fully scrambled when the single fermion that you perturbed has influenced, or let me call it infected, all the other fermions in the problem. Since there are n of them to be infected, it can't go on forever. How long does it take to influence almost all the fermions? Well, you just take the logarithm of both sides of this equation here, and you find that T star is beta over 2 pi times log n. That's called the scrambling time. There is a gravitational or geometric dual of that. It is simply the time that it takes a particle to fall from the hologram, from the holographic degrees of freedom at the boundary to the horizon. If you just work out in general relativity how long, it's almost a Newtonian problem, how long it would take a particle to fall from here to here, it's exactly this. T is equal to beta over 2 pi times log n. So the scrambling time has a simple meaning in the gravitational dual. The gravitational, I really mean gravitational now, it's the falling time from the boundary to the stretched horizon. The stretched horizon just means maybe a Planck distance away from the horizon. Let's come now to de Sitter space. In de Sitter space, there is no difference between the boundary or the holographic boundary and the horizon itself. As I explained earlier, the holographic boundary in de Sitter space is the horizon. And therefore, there is no time that it takes for a perturbation of the holographic degrees of freedom to reach the stretched horizon. The meaning of that is the logarithm is absent. It's the logarithm, which is really the time, the infalling time. There is no infalling time. And one can say that the scrambling time is just basically the radius of curvature of the de Sitter space. No logarithm of n. That time scale is also the time scale for the decay of quasi-normal modes in de Sitter space. And I call that kind of scrambling hyperfast scrambling. It's hyperfast because it is not delayed by the log n factor. Now that's fine. Hyperfast scrambling, I do believe, is the right description of scrambling in de Sitter space, but it violates a rigorous theorem, the fast scrambling bound. Fast scrambling bound was first conjectured by myself and Sakino or something like it, but a rigorous version of it with a precise coefficient here was put in place by Maldacena, Stanford, and Schenker, Maldacena, Schenker, and Stanford. And what it says is that the scrambling time must be bigger than or equal to this beta over 2 pi times log entropy. Entropy is n. Entropy is can be taken to be n. So what it says is that you can't beat the fast scrambling bound, and you can never get to hyperfast scrambling. Well, what goes into the fast scrambling bound? And the main thing, the most important thing, is Q locality. Q locality is, I'm using here in the same sense as K locality. The size of the gates, or the size of the terms in the Hamiltonian. The usual setup for SYK is that Q is fixed while n goes to infinity. Q could be 4. The original SYK theory was Q equals 4. Q equals 6 is fine. Q equals 8 is fine, as long as Q is much smaller than n and kept fixed as n goes to infinity. Here's a little picture of the scrambling process taking place for Q equals 6. Okay, but what happens as in the double scaled SYK system, when Q itself also goes to infinity with n. That was the feature of the double scale theory, that Q squared goes as n. Does the rigorous theorem apply? And the answer is no, the rigorous theorem does not apply. It's completely wrong. So I will give you a little lesson in what happens scrambling in as if Q is allowed to become large in proportion with n, in proportion with the power of n. Here is a little, what is it? It's a rate equation. And what it says is, what is the probability that a given fermionic mode has been corrupted or has been corrupted by the presence of the perturbation at time t equals 0. And what it says is the time derivative, the time here is some appropriate circuit time, the time derivative of the probability that a given fermion has been sickened by the epidemic is just given by 1 minus p. P is the probability, or roughly speaking, the fraction of corrupted modes. 1 minus p is the fraction of uncorrupted modes. And the other factor, 1 minus blah, 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 is the fraction of corrupted modes. So a corrupted mode can corrupt an uncorrupted mode. And that's what this rate equation says. You can solve it, and you find that the probability of infecting, I think the right word is infecting, a particular qubit satisfies this equation right here. Don't worry about the detailed functional form. The point is that it can be calculated, and that's what it is. But let me tell you a little bit about this function. Incidentally, what is P of t? P of t is proportional to the size at a given time, the number of things that have been infected. Well, here's what it looks like for Q equals 4. It starts out at early time, and in fact, it looks exactly like what the Lyapunov, the exponential behavior indicates at low time. And then eventually, as the infection or the epidemic starts to become saturated, it turns over and goes to n. Is there a question? I thought I heard a question.
I'm sorry, Lenny?
Yes.
Sorry, here's your session chair. I have to remind you of the time. I think we have only 2 or 3 minutes left, including the discussion. So it would be great if you could come to one of these stops you prepared.
Yeah, right. I have time, 11:01, 11:03 now. We started at, what time did we start? 10:30, no?
Yes, at 30. And,
oh, yes, you're right. Okay. Well, I'm going to tell you very quickly the end of this story and then postpone for another time the rest of the story, which is quite intriguing, but I haven't got time for it, so we can't do it. I will just tell you the end of the story. Here we are. Whoops. What goes on? You are sharing screen. Yes, I'm supposed to be sharing screen. What's going on? I'm using up my 2 minutes. Go to application. There we go. Okay, you see that there's this increasing exponential time period, which satisfies the Stanford, Maldacena, Schenker bound over here, but then it gives way to something which becomes flat. Supposing you go to Q equals 10, what you find is the same shape of curve, except that the region of exponential growth is squashed down to a smaller time period. And this final exponential behavior takes over much earlier. If you go to Q equals 40, here it is. The time of exponential growth shrinks to something very small. And most of the evolution of the scrambling is following this curve here and not this curve over here. And if you go to Q equals 100, the exponential region of growth has shrunk into almost nothing. The lesson is in a theory in which Q grows with N, the exponential growth region here, I call it the Lyapunov region, shrinks to zero. The Lyapunov exponent behavior is totally irrelevant in that limit. And instead, P grows like e to the minus, well, 1 minus P grows, or it shrinks like e to the minus tau. That's exactly the behavior of quasi-normal modes of de Sitter space. So the implication here, just from this one little piece of information about scrambling, is yes, that there is a close correspondence between what's expected in de Sitter space and what's expected in the double scaled SYK system. Now, the rest of this lecture was to explain what it all has to do with infinite temperature. And I won't be able to get to that unless somebody decides to set up another round of this lecture at some later time. I will not try to go to that now. I will jump to the final conclusions and just spend, do I have 3 minutes to conclude?
Yeah,
if not, I can stop.
Our coffee break, and if I see no protests here in the audience, I think we are happy to give you the 3 minutes. Yes, sure.
Okay, let me suppose that all of this is true. Let's suppose that this type 2 von Neumann algebra story is true. Let's suppose that this double-scaled SYK story is true. What are the implications of it? And in particular, what are the implications for what I started with early about various arguments that have been circulating in the literature for years and years about de Sitter space? Is de Sitter space in the swampland? Well, if this is a genuine and legitimate description of de Sitter space, the static patch of de Sitter space, the answer will be most certainly no. De Sitter space is not in the swampland by explicit example. Is de Sitter space ultra fine-tuned? That is a very interesting question. I think the bottom line is whether a thing is infinitely fine-tuned or not, or very fine-tuned, is a question of whether you're talking about the bulk theory or the boundary theory. It appears in this description here that the boundary theory is not infinitely fine-tuned. You just fix n and you set it, and that determines the size of the de Sitter space. On the other hand, you can ask what are the implications for the coupling constants of the bulk theory. And it looks to me like what all of this would mean is that the bulk constants shrink down to such a small range of possibilities that a small change in the bulk constant would make a large change in the boundary theory, would make a large change, in fact, in the entropy of the de Sitter space. So if you look at it from the point of the boundary theory, it doesn't look like anything's fine-tuned. If you look at it from the point of view of the bulk theory, it's like the dog, sorry, it's like the tail wagging the dog. Try to change the bulk constants a little bit, you will wind up necessarily changing the parameters of the de Sitter space a lot. What does that mean? I'm not sure, but it's a big change. It will be a big change in the way we think about fine-tuning. What about DS being unstable? Many, many people have argued, including Polyakov and other well-known quantum theorists, that quantum de Sitter space is unstable. Well, no, double-scaled SYK system is not unstable. It's a perfectly well-defined unitary quantum mechanics. So my point is that there's a lot at stake here. There's a lot at stake, not only about quantum gravity, not only about de Sitter space, but the nature of cosmology. If I have 1 more minute, I will say 1 or 2 words about what all of this might be relevant in the quantum information world. First of all, it suggests that it's interesting to go beyond Q local systems. By Q local, I mean now where Q or K is fixed, as in gets large. It raises the question, it begs the question, what can be done with Q local quantum circuits where Q is allowed to grow with N? I don't know the answer. I've begun to think about it a little bit, but what are the complexity issues that are involved with circuits in which Q is allowed to grow? That's a very interesting question, which I think, to my knowledge, has not been addressed. Roughly speaking, it says allow your gates to grow with N. The other question is one that I didn't take up here, and I will not continue with. It's about the thermodynamics of infinite temperature. So let me not discuss that. That's it, Renato. I'm finished.
Okay, thanks a lot. Okay, so
shall I come back online or
urgent question, if there is any?
Let me see if I can get back to the. Okay, ask the questions. But, yeah, there are. If there are no questions, I will get back to the committee hearing.
Now I have to ask you to actually come to the stage. We have a new.
So before we go on, I have to ask a question because I want to take up the challenge of Lenny that we could have another session, and I'd like to invite you, Lenny, to give a talk in October or November about the rest of what you have to say in our Tuesday online seminar. And perhaps we even talk about it from the point of view of the von Neumann algebras, and you get a lot of feedback.
I think you should invite Edward to do that.
Lenny, hi, this is Mike Friedman.
Hi, Michael.
I just wanted to make a comment about stability of the bulk versus the hologram. In Euclidean metric, it's a well-known phenomenon in negative curve geometry that hyperbolic space is much more stable than its sphere at infinity. If you perturb from constant minus one.
Yes, I see exactly what you mean. Yes.
Then the metric on the sphere actually doesn't even have smooth coordinate transitions.
Yeah.
After this perturbation away from -1.
Right.
Okay, that's all I wanted to say. Thank you.
No, I'm talking about a different kind of stability. I'm talking about the quantum stability of the let's call it the thermal state.
I suspect the two are connected, actually.
Well, if so, that would be something new to me.
Okay. All right. Thank you.
There is a question on chat, just saying that asking for the reference for this talk.
Okay, so maybe I repeat the question.
Okay.
So there is a question on the chat which I cannot see, but maybe I can open it actually.
So the question says, just a logistic question. What's the reference for this work?
Okay, I won't try to write it down since I'm not screen sharing now, but I can give it to you very easily. The last paper I wrote with Henry Lin was called Infinite Temperatures Not So Hot. And there will be one or two other references to the same subject that you can find there. So just the last paper on the archive by Henry Lin, L-I-N, and myself is, as I said, it's called Infinite Temperature is Not So Hot. And that is, now, it's a work in progress and it's progressing. So we will fairly shortly write another paper, which will in some little ways contradict the previous paper, but nevertheless will add some I think, very significant support to it.
Okay, thank you. So we better read the first paper before the second comes out with the contradiction. Okay.
Well,
so
the contradiction is not really a contradiction. The first papers involved a broader class of possibilities than the strict double-scaled SYK. The next paper will say, if you really want to get the Sitter space in a way that really looks like the Sitter space, you will be forced to the standard double scale limit.
Thanks a
So it's
lot
not really a contradiction.
for joining us even remotely for an inspiring talk. So let's thank Lenny again.
Thank you.